Lesson 5, many body problems. That's the fancy phrase, Nick, for saying, what about more than one mass? So in these problems, we have several objects connected together by strings. The easy approach is to realize that I can actually treat these separate masses as one object since they're all accelerating at the same rate. If I have two objects connected by a string, it's impossible for this object here to accelerate at a different rate from that object there. We're not going to allow you to do that. So we're not going to be allowing you to yank the rope really, really fast or anything like that. The direction they're accelerating will be different. This one is accelerating to your left, while this one is accelerating up. But I'm telling you, if this is accelerating at 2 meters per second squared to the left, that's accelerating up at 2 meters per second squared. That's our first little clever bit of reasoning. Is that okay, Dev? Because of that, we can go like this. We're going to jump straight into it. Example 1 says, find the acceleration and the string tension. You know what? This is a job for a free body diagram. Okay, instead of drawing a separate, don't write this down, free body diagram, because they gave me a lovely picture, I'm actually going to label the diagram that they gave me, which technically, Amy, isn't a free body diagram, because technically in a free body diagram, you're supposed to represent the mass with a dot and redraw everything, but I'm just going to label the forces on the diagram, okay? See that 3 kilogram mass? What are the forces acting on it? Get the obvious one. Gravity. What's the equation that I've been writing for gravity? mg. Is there more than one mass in this question? So I'm going to call this m1g. And I'm going to decide, Cam, from now on, whenever I give you a picture, this is not right or wrong, this is not from a textbook, Max, this is just me being convenient. I'll always read masses from left to right. I'll call the first mass m1, the next mass m2, the next one m3, the next one m4. That's just so that all of our work looks the same, Danielle. It's not a rule, but I'm lazy. Is it sinking into the ground like quicksand? Is it flying into the like Superman? So there's a normal force, and you know what? Since it's mass 1, I'll call it normal force 1, Fn1. Now take a look at this picture. Which way do you think this whole thing is accelerating? Well, the fact that it says mu is 0, which means you're on ice, I think it's going to be accelerating to the right. Okay, you with me so far? Good. What other forces are acting on this 3 kilogram mass? If I said it's accelerating to the right, now a lot of kids want to say, well, that 20 newtons, and I'm going to say no, because that 20 newtons isn't touching the 3 kilogram mass. It isn't touching M1. What's touching M1? A piece of string, a rope. And we're going to give the force from a rope a name, begins with the letter T. Tension. I'm going to go like this. Tension. Is that okay so far, Amy? Those are the forces acting on mass 1. By the way, if there was friction, Thomas, don't write this down. If there was friction, I would have one more force, friction, going that mu times the normal force. I can handle it. In fact, I think later on we'll build up and we'll add some friction. All it does is make the question longer, really not tougher. Let's go to mass 2. What are the forces acting on mass 2? Get the obvious one. I'll call that M2G. Spence, is it sinking into the ground like quicksand? Is it flying into the air like Superman? So there must be a normal force pointing up. Normal force number 2. What else? You know what? This 20, we'll call that the applied force. Someone's tugging on it, or a horse is pulling it, or a car is pulling. I don't know, but there's some kind of outside applied force. There's one more. And this comes out of Newton's third law, which said that forces come in on any rope. There's always a tug on both ends. It's actually a lovely example of Newton's third law. I defy you, Colin, if you and I are having a tug of war, I defy you to exert a different force than all feel. It can't be done. Whatever force you exert, I'll feel through my arms. Whatever force I exert, you'll feel. In fact, the tension is going to be the combination of both of our forces, but it's going to be the same throughout the whole rope. Okay? There it is. Which way is this accelerating, do we think? Up, down, left, or right? Right. Who's winning? Same answer. To the right. Which force would be the winning force then? The applied. What I'm going to say in my equation, Justin, is any force that ends up pointing to the right is going to be winner plus. Any force that ends up pointing to the left is going to be loser. Sorry, didn't mean to look at you. Loser minus. You ready? So I'm going to walk down. Oh, vertically everything's balanced. Can you see, Ange? But horizontally, I'm going to walk along the string. Who's winning? And then as I walk along the string, I walk along the string, I walk along the string, I run into tension. Now, which way is tension here pointing? Loser! Sorry, the force, not you. Keep walking, keep walking. Oh, I also run into this force. Which way is it pointing? Winner. Are there any other forces along the string? No. Equals. What always went on the right-hand side? The only change we have to make is, have we looked at more than one mass in this question? Mass of both times A. That's the only tweak. We treat it as though it's one big ubermass. We pretend they're glued together. What do you notice on the left-hand side about tension? Carson, they cancel out. I always make the joke, I find these questions so relaxing because you always lose tension. Oh, sorry. No? Okay. Right? Negative tension plus tension is going to vanish. What did this question want me to find in the very, very first line? Two things. What was the first thing? Acceleration. How would I get the A by itself? Divide by the mass of both. Okay. So I'm going to get this. Acceleration is going to be F applied divided by M1 plus M2, because that's what the mass of both means. Don't times them. You add them together. Every year I see a couple of kids that want to times them. No, both would mean add them up. Jordan, keep going. What's F applied? As a number, they told me in the picture. I hope, yes? 20. Jordan, keep going. What's mass 1? What's mass 2? I would argue that you actually can do this without a calculator. Don't reach for it. You weren't reaching for your calculator. No, of course not. Because Riley, what is 3 plus 2 in your head? 5. And what's 20 divided by 5 in your head? So you don't need no stinking calculator. 4 meters per second squared. I guess 4.0, because it looks like they went to 2 sig figs in all the data. But I wouldn't take marks off if you just wrote 4. We're only half done. Kyle, what else did they ask me to find in this question? They said find the acceleration and tension. So here's going to be our strategy. And if they give me more than one mass, I'll find acceleration by saying, yeah, they didn't give me more than one mass. I'll treat it like one big uber mass. I'll do all of my individual forces on the left side, but it's going to be winner minus loser equals the mass of both times A. Or if there's 3 masses, the mass of all 3 times A. Or if there's 4 masses, the mass of all 4 times A. But then, to find any individual forces, I will go look at individual masses. So I wrote here, to find the tension, we look at a single mass. Consider the 3 kilogram mass. Remember, Justin, the forces were M1G, normal force 1, and tension. Is that right? I've scrolled down, but that's what we had on the 3 kilogram mass, yeah? Let's just write an equation, Colin, only for that mass. Ignore everything else. Looking at that mass, which direction is it accelerating? So who's winning? Tension. Who's losing? It's a trick question. Is there anything pointing to the left on mass 1? So who's losing? Nothing. So I can now, looking at one mass, I can say this. Tension equals. Are we looking at one mass or both masses? Right now, in my equation, am I looking at one mass or both masses? Amy, say one. So you know what? It's going to be M1A. So it's still MA, but now I modify it again, Riley, to say, no, I'm one mass. Do I know mass 1? 3. Did I just figure out the acceleration in my head without a calculator? Well, hey. You know what the tension in the rope is? Riley, keep going in your head, please. 12 what? Tension is a force. Newtons. Newtons. Wait a minute, Mr. Dueck. What if instead of looking at mass 1, what if I had looked at mass 2? Okay. What were the forces acting on mass 2? If I recall, it was M2G. You guys can correct me. It was normal force 2. We had the applied force, and then we had tension this way, right? I think? Is that correct? Okay. Looking at mass 2, who's winning? Is there a loser? Tension pointing to the left. Are there any other forces along the rope for mass 2? Don't see any. It's going to be M2A because I'm looking at mass 2. Let's find tension here. Now, to do that, what's immediately in front of the tension? A negative. So, what could I do to make that a positive? Okay, we've seen this trick before, I hope you remember. I'm going to plus it to this side, and I usually just draw an arrow like that, and I'm going to minus this to this side, and if you want, you can put a little minus there to remind yourself that you're minusing and that you're plussing. But I think I'm going to get this. I'm going to get F applied minus M2A apparently equals tension. Is that okay? So tension equals, Justin, my friend, what was F applied? They gave it to me in the diagram, I think. What was it? How big? Psst. 20. Yep. Oh, try that again. You said 20, right? Minus, and what was mass 2? They gave it to me in the picture as well. How many kilograms? 2. And Justin, what did we figure out the acceleration was a couple of lines ago? Got to go back and find it. What did we say the acceleration of this was? That's a force. Go back further. What did we say the acceleration was? Squared. 4 meters per second squared, right? And that's how I know it's an acceleration. Yeah. Hey, we can do this one on our heads too. Justin, what's 2 times 4 in your head? 8. 20 take away 8 is? Holy smokes, I get the same answer either way. Right? Which hopefully mathematically, Colin, convinces you that that argument that I said you and I, if we're having a tug of war, can't possibly exert different forces on either end. There's the mathematical proof. Now, you'll notice one of these equations was easier. Usually what I do to solve for tension is I try and find the mass that tension is a winner on, because it's easier to get it by itself. Here, where tension was a winner, it was easier to get it by itself. Here, where tension was a loser, well, it's got a negative. I'm always going to have to plus it over to I'm going to have to do some algebra. But it doesn't matter. In fact, you know what? On a test, if I had time, I might do both and get a little nerdy smile when I get the same answer for both, because then I know I'm right. I have to be. What's our strategy, Cam? If they give me more than one mass, I'm going to treat it like one mass. I'll figure out who's winning, Anything in that same direction will be winner plus. Anything in the opposite direction will be loser minus. And it's going to equal the mass of all of them times A. Both if it's 2, all of them if it's 3. I can even do it if we got something hanging over a cliff. So I wrote here, if we have a hanging mass and no other external force, then we need to understand that it's the weight. Hey, when I say weight, what does weight mean in physics? Boy, if you had a good physics teacher, he would have gone on a rant about that about 5 minutes before the lesson. When you see this, what does that mean? You said it, Amy. I saw you. mg, okay. It's the weight, it's the force of gravity that accelerates the system. In other words, example 3. Is there friction in example 3, and how do you know? How do you know there's no friction? How did I show you that in the diagram? Okay, I'm going to do that because these diagrams are a pain to do in Word. I generally make one and then I cut and paste and just change the numbers, okay? So mu is 0. This is on ice. So you know what? If this was ice and gravity was tugging this guy down, you know what? Everything is going to slide. What direction is this guy going to slide to? The right? What direction is this guy going to slide? Down. Okay. It wants me to identify the net force. We're going to do that in our in our diagram, but we're going to then find the acceleration and the tension. Let's do this. What are the forces acting on this 2 kilogram mass? Get the obvious one. Which way? Straight down. And I'll call that M1G because Danielle and more than one mass. Is this mass sinking into the ground like quicksand? Is it flying into the air like Superman? You know what? There's a normal force. I'll call it normal force number 1. What else? You guys told me it's accelerating right, and right now that would be impossible. There must be an unbalanced force pointing to the right. What's causing it to accelerate to the right? The string, which we call tension. So far, so good, Thomas? Let's keep going. Oh, by the way, if I did, as an advanced question, Amelia, include friction, I would have one more force, friction pointing that way. It would be a loser. It would be a minus friction, and it would be mu times the normal force. I don't know the normal force. Oh, but look. I don't know the force the same size. I can handle it. This is why I said earlier, if I add friction, the question gets longer, not really much tougher. Mass 2. What are the forces acting on it? Get the obvious one. Gravity, which way? Straight down. I'll call that M2G. Is this mass touching a surface? No. So is there a normal force? No, not if you're hanging in midair. What else? It's not in free fall, so something must be slowing it down. Oh! Pointing straight up. In fact, what that pulley does is allows the force to go through a 90-degree bend. So here's the question. Which is winning? Which force is the winning force? Which is the force that's causing everything to occur? I think this. This pulling down is pulling that sideways. So now I'm going to walk along the whole rope, turning the corner right here. Anything that ends up pointing down when it gets over here is going to be winner plus. Anything that ends up pointing up when it gets over here is going to be loser minus. This is a terrible lesson to be doing on Pink Shirt Day because I keep emphasizing the word lose. Anyways, just get it to stick. Okay? So who's winning? Right? Now, Justin, we're going to walk along the rope. And anything that points down, Justin, is going to be winner. Anything that points up is going to be... Okay? Ooh, so this tension is a... Don't insult it, but it understands. Now, when I walk over here, this tension is horizontal. I need to follow it until I get on the same plane, the same piece of string as gravity. Which way would this tension end up pointing when it got over to here? So it makes it a winner. Are there any other forces on the string? Now, common mistake, kids want to put M1G. Is it along the string? Nope. In fact, m1g is canceled out by normal force number 1. It's irrelevant to this question. However, have we written forces from more than one mass? Then it's going to be m1 plus m2 times A. Last time I wrote m both, and that's fine. Or you can actually write them out, m1 plus m2 in brackets times A. Why is Mr. Dueck so relaxed? Because he's losing tension, baby. Always. I find these questions so relaxing. Mr. Dueck, will tension always cancel? Most of the time. Do we have to write it? I encourage you to, both for the nerdy, giddy thrill of saying to yourself, oh, I'm relaxing and losing tension, but also it's just good physics. Takes 1 second. What do they want me to find? Oh, by the way, it says identify the net force on the system. It's that part of the equation. So I said I take care of that in my free body diagram. So I'm not worried about that. What do they want me to find? Oh, how would I get the A by itself? Divide by the bracket. Yep. So you ready? A is going to be m2g divided by m1 plus m2. Cam, what's M2? 4? What's G? Hopefully we have that memorized by now because it's so convenient. What's G? Folks, what's G? 9.8. Negative? Nope. This is why I said in this unit we're going to often find it's more convenient to let down be positive, which we have this time. And you can kind of see why. It gives you a much nicer equation. So I'm just going to put 9.8 over. Cam, what was M1? 2 plus 4. Is there more than one number? Now, you can either do the bottom in your head, because, Cam, in your head, what is 2 plus 4? You could just divide by 6. Or if you don't, is there more than one number in the bottom? You better put the bottom in brackets. What's the acceleration?
Do this one in your head, Mr.
Oh, maybe I can. 4 over 6 is 2 over 3, so it's going to be 9.8 times 2, which is 19.6, divided by 3. It's going to be 6.7 something? 6.5 even?
No, 6.53.
5.3 repeating.
Yeah.
Ah, I was off. What are the units for acceleration? Meters per second squared. Okay. You know what? I tend to put a box around things that I found an answer for. Yay! That's kind of like my touchdown spike. We're not done. Amelia, what else did they want me to find? They said find the acceleration and... You know what? To find tension, let's look at one mass. Which mass do you want to use? We can use mass 1 or mass 2. Doesn't matter. Mass 1? Okay, so I'm not going to redraw. Do I? Yeah. Oh, to find tension, I wrote here, isolate one mass. I guess I did have space over here. Okay, fair enough. So we had M1G, normal force 1, and tension. Right? Who's winning? First of all, which way is mass 1 accelerating? To the right. So who's winning? Tension. Who's losing? Nothing. So my equation is going to be winner equals, what's it always equaled on the right-hand side? Some variation of MA. Are we looking at one mass in this particular question? So it's going to be M1A, because we didn't look at both. And you'll notice, holy smokes, I already got T by itself. It's going to be 2 times 6.5333333333333. 2 times 9.8 divided by, actually 4 times 9.8 divided by 6. That was the acceleration, right? So now I'm going to go use your answer button if you can, which is why I went on the rant about getting a good calculator. So I'm going to go times by 2, and I get 13 point, I guess, 0.1, right? Spence, is that okay?
Oh, no, I was just thinking.
Yeah, I can tell because you're going
No, you know how you put 4 at the beginning?
4 at the beginning.
Calculator.
Oh, on my calculator?
Yeah.
So here's what happened. I hadn't typed this equation in yet, so I very quickly said I wanted that on my calculator, so I did the last quick question quickly because I wanted to use my answer button, and I figured it was going to be about the same number of keystrokes to type that and have it accurate to like 50 decimal places than it was going to be to type 6.5 and a few threes. I'm a nut about trying to be accurate, and anytime I can use my answer button and carry a number over without rounding off, I will. That's all. Good question. Hey, you know what? Just for giggles, let's try it with mass 2. What were the forces acting on mass 2? I'll draw a free body diagram. It was M2G and tension, was it not? I'll go back and, yeah, right? M2G and tension, and M2G was the winner. So let's write an equation for mass 2. Who's winning? Who's losing? And that equals M2A. Let's find tension here. Kyle, what's immediately in front of the tension? Immediately in front of the tension, right? Immediately right in front. Yeah, don't overcomplicate it. A what? So it's plus. We've seen this trick before. Plus it there at the same time, minus that there. That's the quick way to get it by itself. And I get M2G minus M2A equals tension. I think mass 2 was 4 kilograms, right? If I go 4, hey Cam, what's G? Yeah, thank you. You were a little slow last time. That should be right up here. Minus 4 times 6.533. I'll add a few extra 3s. If you type that in, do you also get 13.1? You might get 13.0 or 13.2. There might be some rounding off, but I'm pretty sure you get really close to 13.1. Do you? So, doesn't matter which one you pick, although usually one of them will be considerably easier. Well, usually the one where tension is the winner. For problems that involve friction, we can still use the system approach to find acceleration, but tension calculations can be a little bit trickier. I wrote we'll do this in Physics 12. I'm wondering why I wrote that. I thought maybe I had some later on with friction. I might sneak it in Physics 11. We'll see. We'll go about 10 more minutes and then press pause. The Atwood machine. It's a fancy name for something that's very commonplace. An Atwood machine is a pulley system as seen below where two masses are hanging from gravity. You know what? Look up. If this was a good pulley, this is an Atwood machine. Oh, except we're in our magic physics world because this pulley has no friction. And this pulley has no mass. And these ropes have no mass because all of that would give me yucky math. But it's a good thought experiment to work with. The Atwood machine. Mass 2, this one, makes it easier for a person or a motor to lift mass 1. In fact, mass 2 is often called a counterweight. Elevators all work like this. All elevators off in a secondary shaft next to the main elevator have a weight that's exactly the same mass as an empty car. So that all the motor is lifting or lowering are the people, not the car itself. It's a smart system. Question. Suppose we have equal masses on both sides of an Atwood machine. Equal masses on both sides of an Atwood machine. And one mass is lifted higher. For you guys, it's this one. Okay? And then I let go. So if they're equal masses and there's no friction here, and this mass is lifted higher, and I let go, how does the system move? Now this remains at rest. It's friction. A, does it remain at rest? B, does the higher mass fall lower? Or C, does the higher mass go higher? So you understand the thought question? Okay? We're going to take an Atwood machine, we're going to raise one mass higher, and we're going to let go. When I let go, is it going to remain at rest, fall lower, or go higher? You know what? Since there's three choices, I think once again, we can vote. Once again, how high you hold your hand up is how sure you are of the answer. Let's pause the video for a second. So my class has voted. And everyone went with C. I've never had that before. I usually have about a three-way split. Can you read to me, Oscar, that line right there?
Explain your answer.
You missed the key phrase.
Using
principles of physics. Okay. You know what one of our better tools in forces is to analyze stuff like this? How about a good free body diagram? How about we label the forces? So I'm going to label the forces in this picture right here. Okay? What are the forces acting on the left-hand mass? Get the obvious one. Is there a rope? Oh, so tension, up. Right? What are the forces on the right-hand mass? Oh, is it touching a surface? So is there a normal force? No. And we've decided this is magically a frictionless pulley. Okay. What are the forces on the right-hand mass? Get the obvious one. Gravity. Are these masses identical? The question does say that. So I'm going to write mg again. I'm not going to call them m1 and m2. They're both m. Is there a rope? Okay. So you guys all voted C. You said the higher mass goes higher. So if I hear you correctly, if this is going higher, this must be winning. So let's write an equation so that anything that ends up pointing down on the left is going to be winner plus. Anything that ends up pointing up on the left is going to be loser minus. Okay? I see a few of you starting to think, So winner. This tension here, winner or loser? Now, this tension here, you might say it's pointing up, it's a loser, but look, if you follow it, follow it, follow it, follow it, follow it, follow it, when it gets to this side, which way will it be pointing? Down, making it a winner plus. I just relaxed. I don't know about you. Okay. And this mg here, now you might think it's a winner because it's pointing down, but if you follow it, follow it, follow it all the way over, when it gets to this side, which way will it be pointing? This will be pointing downwards?
No.
Upwards, I think, right? You got to use your imagination, but I think it would end up pointing up on that side. Is that okay, Kyle? So we'd have this equals, have we looked at more than one mass? Yeah, it equals m1, since both masses are the same, how about 2m times A? Right? Oh, what else are you seeing there on the left? In fact, as a number on the left, I get this. That apparently equals 2 times m times A. When you multiply and get 0 as an answer, the only way you can do that is if one of these is 0. Are the masses 0? So what must be 0? So now that you see that, does anybody want to revise their answer? Anybody want to revise their answer? Devin? Has to be. And by the way, what a lovely proof. Did we use any English? Did we write any words? We did a picture is worth 1,000 words, and we got an equation, and we proved it. You can't argue with me. This is not an opinion. This is fact. It says, using principles of physics, explain your answer. I'm going to draw there, right there. Right there. Okay. Really, by the way, what we're saying is this is Newton's first law again. There are no unbalanced forces, so it can't possibly be accelerating. Now, if I had said part D, if I'd given you an option D keeps moving at a constant speed, that could be possible. But that we said it started at rest. So if it starts at rest and it can't accelerate, it must stay at rest. It must. Okay? Which, again, is great for elevators, because that means when an elevator stops on the 5th floor or the 10th floor and everyone gets out, as long as the elevator isn't moving and there's that counterweight that exactly matches the empty car, we're not burning any electricity. We're not using any power. It can stay up there just fine. How much more am I going to be doing? I got 1, 2, 3, 4, 5, 6. So I think what we're going to do now, temporarily, so right now, finish the take-home quiz. You can also work on applications of Newton's second law, but I got a couple of videos to show you too.